Hello everyone, my name is Semm. I'm from Good Karma. My another two members are Wijing Shun and Azul bin Danin. So today I'm here to present about the group project about the constant strain triangle analysis. Next, I will give some introduction about this group project. So in this group project, we need to use the finite element analysis to determine the displacement stress and strains on the thin plate, and then the analysis can be done by using the finite element analysis software, and since with a list of 12 triangular elements, then the obtained results to the quantum motor can be used for the entire surface of the plate. Okay. Besides that, we also can do the comparison with the analysis result that obtained through the octave. Next, so our objective of this group project is to apply the knowledge learned to the CST element and then do the finite element analysis on the thin plate. Second, to solve the FEM model by using simplified element in appropriate boundary condition by using scenes and manually. Lastly, the objective of this project is to apply the team working skills in order to solve the problem faced. Okay, next. So now I will explain the paradigm inside this group project. Okay, in this study, this data were given. For example, the Young modulus E is equal to 207 G Pascal, and then for the Poisson ratios, the V is equal to 0.3, and then the ratio of R per D is given in 0.25, and then a ratio of W per D is given in 1.2. So based on the data given, we have some assumption on the value. For example, the R is equal to 5 cm and the W is equal to 24 cm, and then for the D is equal to 20 cm, and lastly the L is equal to 20 cm also. And then, okay, as you can see, we have choose the top left photo body for the whole thin plate for the analysis. So the result calculated actually is same for the entire body of the thin plate. And then we have labeled some points, for example, point A, point B, and point C on the quantum motor so that easier for our calculation. Next. So in the problem modeling, we have choose the plane stress condition. This is because the geometry of the quantum motor is quite thick in compared to the entire area of the model. Okay, so while we setting the appropriate boundary condition, okay, we fix the point on the bottom right is the fixed support part. So this is a point D, is a fixed support part. Okay, and then at the left hand side, at the bottom left hand side, we set the axial tension force, which is 100 Newton, and this axial tension log is point C, and we set it here. Okay, so lastly, the roller support is needed to set at this bottom part and the right hand side part of this quantum model. Okay, this is our bottom modeling while we setting the appropriate boundary condition. Next, so this 15 element as since analysis result. Okay, so this one is the result for the x directional deformation, and then the minimum x directional deformation is at here, and then the maximum x directional deformation is at here. Okay, so for the results of the x directional deformation for point A, point B, and point C is at here. Okay, point A, point B, and point C. The result will show in the table at the next slide. Okay, for the y directional deformation, this is the result. Okay, is the maximum y directional deformation and the minimum y directional deformation. And then for the results of the y directional deformation at point A, point B, and point C is here. Okay, point A, point B, and point C. Okay, the results will show in the table at the next slide. Okay, so for the This is the result for the normal stress. Okay, this is the minimum normal stress, and this is the maximum normal stress. Okay, for the results for normal stress in point A, point B, and point C is shown at here. Okay, so the result will show in the table at the next slide. Okay, so for the result of the normal elastic strain, okay, so this is the minimum normal elastic strain, and this is the maximum. Okay, if you want to find the magnitude, again you can read it here. Okay, so for the results of normal elastic strain for point A, point B, and point C, okay, will show in the table at the next slide. Okay, next. So the result of the x directional displacement and the y directional displacement and the stress in x directional and in y directional and the strain in x directional and y directional is shown here. Okay, so this is the results for the point ABC in the displacement, stress, and the strain. So next, I will pass my slide to my next teammate. Okay, thank you.
Right. Assalamualaikum and hi, my name is Azul Dani, and I'll be expanding on the analysis of the CST case study by using the Octave software, where in this part we'll be looking at how it will affect the result of our analysis in compared to the NC software that have been explained in the first part before. Alright, directly to the point, the first thing that we need to do is declaring all the functions and values of the properties that we know or using. And then for this next part is we'll be assigning the first phase of our boundary conditions according to the elementary distributions generated from the ANSYS as we want to compare with the same reference points of conditions, where from it we'll get 14 nodes, 15 elements, as well 3 nodes per element and 2 degrees of freedom for each node. And of course, we need to assign this initial condition of the coordinates for each node in the form of matrix to save them in their own array from this ANSYS generated results. And then now we need to declare the nodal connectivity for each element that we have set in our case, which is like this one. In the first element, the first local node is the 13 or node 13, while for the second and third local node, we will be using the 4 and node 12. And then next for our second phase boundary condition from the same condition of the analysis in the ANSYS, we'll be declaring that node 2 is a fixed point causing no displacement at all, while N5 and N6 will act as a roller that only move in y directions and causing no displacement in x directions, while in the node N1, N3, and N4, it will be acting as a roller too, but will be moving in the x directions and only causing displacement on the x-axis. Alright, and then now is assigning the applicable force, which in this case will be at the node C or node N1 with 100 Newton to the negative direction of the x-axis. And then is about to assemble it to the global force vector for only the point load. And then next part is we'll be using these two local functions here as we want to reuse them again without worrying too complex code to debug later on, where the first function is to solve the strain displacement matrix B, where firstly we need to assign the node with respect to their nodal conductivity for each element, like this one is the first element I is referred to the element first. The one is node 1 and can be 2 or 3 for the other local node, while the 2 will act as y coordinate and for x coordinate will be using 1. And then this one will be using to solve the Jacobian matrix J. This one is for the elementary area, and this one is for the B matrix. And then for the second function, we'll be needing it to solve the assemble global stiffness matrix, where the main interest is with the k element as the element stiffness matrix to be used to assemble the global stiffness matrix. And then from this one, To find the unknown displacement q, we'll be using the equation right here, where from the derivation of the Hooke's law and multiplying both sides with the inverse of global matrix K, we can get the q in terms of the matrix. And then lastly, for the comparison, we'll be using this percentage difference equations, where A is the value from the ANSYS and B will be the value from the octave that we got. However, for this case, we'll only be looking at the point not 1, not 5, and not 7. And then now as for the results, where for the three values from the octave and ANSYS, we got 0% differences for both displacement at node 1 and 5 for the x directions, while 0.12% of differences shown for the x displacement at node 7. This sure is a good result as it is similar to the results generated in the ANSYS. However, for the case of the both stress and strain, we got a big percentage of difference. All of this difference might be or can be assumed coming from the either miscalculations or wrongly coded in the octave, as well could be coming from the simulation from the ANSYS itself, as it is considering a real world physical condition like the gravity. And with that, thank you.
Hi, I'm Jingsun and I'm going to present about the discussion and analysis of ANSYS using more than 15 elements. So it's obvious that the more the number of elements used, the better the subject is able to resemble the actual model. However, the improvement in error has a diminishing effect as the number of elements increases. Hence, the optimal number of elements are to be determined. Since the software utilizes the length of element to draw the model, the closer the approximation obtained to the actual parameter, the better the constant strain triangles are able to represent the actual structure. An error of 0.5% from actual parameter would be optimum number as theoretically, the further increase in elements will only bring little and diminishing improvement in the final answer. The following assumptions were made. The average error of each element would be length of element power 2 divided by 2. The smaller the difference of parameter obtained compared to the actual parameter, the better the element will be able to represent the actual shape. Comparing the results from 749 elements and 15 elements, it could be seen that the values are generally far from each other except for displacement A, which are 0 for both analyses. This is because the shape to be analyzed is of irregular shape and it could not be closely represented by triangles. Comparing the first and last picture to the original model, it could be seen that the difference between 15-element model, 749-element model, and the original model are getting smaller. From calculations, it could be seen that the Poisson ratio value is far from the one used for analysis. This is probably because the geometry of the studied model is not rectangular. With the complex dimensions used in analysis, the model would no longer be able to follow the Poisson's ratio of 0.3. There's an error of 141% compared to the graph, which is significant. This is probably because the stress should be average stress, and average stress could only be represented by force divided by area when the circular segment is insignificant compared to the entire model. Further analysis is needed in order to determine the actual value for average stress. Besides displacement at the fixed support, all other calculated parameters were not consistently converging with the number of elements increased. It is noted that although the consistency generally increases with the increasing number of elements, the result might still experience a spike due to the number of elements unable to match the geometry in a more precise manner compared to a lower number of elements. Therefore, it is important to carry out analysis with plus minus a few elements near the chosen number of elements to obtain the better result. In conclusion, higher number of elements generally produce result with higher accuracy, but to make sure the elements are not distorted due to their number, analysis with a fraction of elements fewer or more is needed to be done. Finite element analysis is a simplified way to approximate the actual stress, strain, displacement, and other components. Modeling could be simplified if the subject is symmetrical with appropriate boundary conditions. With the aid of software and ANSYS, all triangles method could be used to simplify the calculation, making analysis with more elements possible, thus yielding results with higher accuracy. However, the use of more elements does not always result in an increase in accuracy due to the actual geometry of the model. Therefore, analysis should be done with progressing number of elements to avoid such errors. Although the optimum number of elements were calculated due to the improving computational power in recent computers, users could just increase the number of elements for higher accuracy. That's all from us. Thank you.